Hello, Math 137 people. Welcome to Chapter 9, Rational Expressions. Today we're going to talk about the basics in simplifying rational expressions. So just a reminder what a rational number is. A rational number is any number that can be written in the form, any number that can be written P over Q, so in fractional form where P and Q are integers. Okay, and reminder what an integer is. Integers are your counting numbers, 0, 1, 2, 3, 4, forever. But they're also their negative counterparts, -2 forever. So it's all your positive counting numbers and all your negative counting numbers in 0. So examples of rational numbers would be 3/7, integer over integer. An example of a rational number, 4 is a rational number because we can write 4 is 4 over 1. We could also write it as 8 over 2. 0 is a rational number because 0 can be written as 0 over 1 or 0 over 4, right? Finite decimals, 0.6 is a rational number because we can write 0.6 as 6/10, right? We could have negative, 0.333 repeating because that can just be written as -1/3, so forth and so on. So what numbers are not rational? Not rational would be examples like, well, not rational means it's not a rational number. Examples. Pi is not a rational number. There is no fractional equivalent for pi. Square root of 2 has no rational equivalent. The number e is a number like pi. It's an irrational, infinite, non-repeating decimal. So forth and so on. So today we're going to talk about rational expressions, define what a rational expression is. A rational expression is a ratio, instead of numbers, it's a ratio of polynomials. So that is, you're going to have a polynomial over a polynomial. So I'm going to say polynomial 1 over polynomial 2 because they typically are different. What is a polynomial? Well, if you need a review of polynomials, see Chapter 5 for more details, but I'll give you an example of a polynomials. An example of a polynomial is x squared plus 3x minus 6. This is a second degree polynomial because the highest power on the variable is 2. What makes a polynomial is the power on the variables all are non-negative integers. So here x has the power of 2, here x has the power of 1, we don't see it. And technically we call this the 0th degree because x to the 0 would just cancel out and become 1. So this is an example of a second degree polynomial. So all quadratic equations are second degree polynomials. 4x minus 10. All linear equations are first degree polynomials. We could have -6x to the 5th plus 4x cubed plus 2x plus 10. This would be an example of a 5th degree polynomial. Now polynomials don't have to have every power below the highest power. Notice there's no 4th degree here, 4th degree term here, but this would be a 5th degree polynomial. The powers on the variable are 5, 3, 1, and 0. Okay, so what is not a polynomial? So examples of things that are not polynomials, what you have to look for, what would be an example of something that's not a polynomial? Well, we could square squared of x plus 5 is not a polynomial. Because remember, the square root of x is equivalent to x to the 1/2 power plus 5. So we can write radicals as powers, but in order for it to be a polynomial, the power has to be a whole positive number or a whole non-negative number. So 1/2 wouldn't work here, so not a polynomial. So radicals, variables under the radicals are not polynomials. If we had 4 over x squared plus 2x minus 10, this is not a polynomial. Because even though we have, it looks like we have a power of 2 and a power of 1, be careful because this is equivalent to 4x to the negative 2 power plus 2x minus 10. So the problem would be right here. The power on the variable has to be positive. So writing 4 over x squared doesn't make the power on the variable positive. It just puts it in a position to be more visually pleasing, but it really means 4x to the negative 2. So we can't have variables in denominators or fractions in polynomials. All right, so going back to polynomials, polynomials are nice, well-behaved. All the powers on the variables are positive integers or non-negative integers because constants themselves are polynomials. The degree would technically be 0 here. So remember, what we're trying to define eventually is what a rational expression is. So a rational expression is a ratio of polynomials. So examples of rational expressions would be, I don't know, what's your favorite polynomial? X squared minus 2x plus 5 all over x plus 1. So that's a second degree polynomial over first degree polynomial. We can have constants over a bigger expression. So that's a 0 degree polynomial over a second degree polynomial. Right, we can have anything we want. X to the 5th plus x to the 4th plus x cubed plus x squared plus x all over x plus 2. 5th degree polynomial over first degree polynomial. All right, so what are we going to do with these? Well, it depends on the problem. Let's give you a friendly reminder of the difference between, just do that, the difference between expressions and equations. All right, well, what is the difference between expressions and equations? Well, in equations have an equal sign, right? Expressions don't have an equal sign unless we insert them. What we do with expressions, we simplify, maybe rewrite them in a different form like factor. We may evaluate an expression, like maybe the expression is x plus 2, and it says, what is the value of the expression? X plus 2. Well, we can't simplify that. We can't factor it, but I could evaluate it. If I said, what's the value when x equals 7? We'd get 7 plus 2, and it equals 9. So just because we inserted an equal sign didn't make what we started with an equation. We just put the 7 in and got the output. So we evaluated this expression. An equation has to equal some value, and the difference between equations and expressions is we solve equations. So we may have something like x minus 3 times x plus 2. Now, if I left it like that, it would just be an expression, but let's say I set it equal to 0. Now we're trying to find the values of x that make this a true statement. Well, the first factor would tell us that 3 is a solution, and the second factor would tell us that negative 2 is a solution. So these are solutions to the equations. They're numbers that we would insert, and it would make the equation true. This is, we really just, this is the answer to this problem. It's not really the solution because we didn't solve for it. We assigned a value for x and we plugged it in and got the output. All right. So this is what we're going to talk about today. We're going to look at expressions. So we're going to simplify, factor, evaluate, and we will solve rational equations a little bit later in a further section in this chapter. All right, given the expression x plus 1 over x squared minus 9. So this is a rational expression. It is a first degree polynomial, a second degree polynomial. It says evaluate for each of these 4 values. So I'm going to start with 0. I'm going to plug 0 in. I get 0 plus 1 over 0 squared minus 9. Well, 0 plus 1 is 1. 0 squared minus 9 is negative 9. So the answer is 1 over negative 9. We could put the negative out front and call this negative 1/9. Either one of those are perfectly acceptable answers. And we just make sure, can we simplify this at all? And we can't. 1/9 is in its simplest form. All right, let's try 1. We put 1 in, we get 1 plus 1 over 1 squared minus 9. That's 2 over negative 8. All right, now this answer is not, we're getting there, but it's not the final answer because always we want to simplify. So 2 over negative 8, I'm going to pull the negative out front, and 2 over 8 simplifies to 1 over 4 because we have a factor of 2 at 8, right? So remember, I can think of this as 2 times 4, and then the 2's cancel. So we just get negative 1/4. All right, how about x equals negative 1? Negative 1 plus 1 all over negative 1. Now be really careful here because we're squaring the entire number negative 1. So the numerator is going to be 0 and the denominator is going to be 1 minus 9. We're going to get 0 over negative 8, which is 0. We are allowed to have 0 in the numerator. We're not allowed to have 0 in the denominator. If we have 0 in the numerator, 0 over a non-zero number is just 0. If we had 0 over 0 or a non-zero number over 0, it would be an undefined number, and we would just say undefined. Right, so at negative 1, the output is 0. We are allowed to have 0 in the numerator. All right, last one, 3. We're going to get 3 plus 1 all over 3 squared minus 9. We're going to get 4 over, Okay, we're not allowed to have 0 in the denominator. 4 divided by 0 is undefined. If you have Siri, ask Siri what 4 divided by 0 is. It gives you a cute little answer. Do it on your calculator. It'll say domain error or no real number. It'll say all sorts of funky stuff like that. So when we have a situation like this where we have a number, notice 0 went nicely and it gave us an output. 1 went nicely in, it gave us the output negative 1/4. When we put negative 1 in, we got the output 0. But when we put 3 in, we got something that didn't work. It was undefined. We're not allowed to put 3 into this expression. So note, we call 3 a restricted value for this expression. We are not allowed to put 3 in it because it does not produce an output. So we call 3 a restricted value for the expression. That is 3, x equals 3 is not allowed to be used for an input. Right, so often we're interested in the restricted values. To find the restricted values for a rational expression, we find the inputs that would make the denominator 0. So find the values of the input that would make the denominator equal to 0, because denominators in rational expressions are not allowed to be 0. Right. When looking for restricted values, we are looking for the real zeros of the denominator. So I know we talked about imaginary numbers in chapter 7. We're not using i's here, so if we come across a situation that only imaginary numbers make the denominator 0, we don't count them. We're just looking for real inputs that produce an output of 0 in the denominator. So let's go back to our expression, x plus 1 over x squared plus 9, the restricted values. From now on, I'm just going to abbreviate that RV for restricted values. So to find the restricted values, we set the denominator equal to 0. So what would make x squared minus 9 equal 0? Now this is pretty obvious. You might see that it's 3, but don't forget that it's also negative 3. So you can factor this. This is just the difference of squares. right? So we get the two factors, 3 and -3. Or you could have done, just for a friendly reminder, you could use the square root property. It's something squared equals a number, so that something equals the positive negative square root of that number. So positive -3. So either way, the restricted values for this expression, x plus 1 over x squared minus 9, or any rational expression with x squared minus 9 in the denominator, the restricted values would be 3 and -3. That's it. Not too bad. Right, let's look at this rational expression. Find the restricted values for the rational expression. X squared minus 4x plus 7 over x minus 10. We'll find the restricted values. Set the denominator equal to 0. So clearly we have one restricted value here. So therefore the only restricted value for this expression is x equals 10. All right, so now for a minute, let's think about this. The only number that's going to create a 0 in the denominator is 10. We can put any other number into this expression and get an output. So that being said, we're going to define the domain, or we're going to find the domain of this rational expression. Remember, the domain of any expression is what you're allowed to put into this expression. We're not allowed to put in 10, so we can put in any other number. So we can use any number except x equals 10 as an input for this expression. Thus, the domain is the allowable set of inputs. The domain of x squared minus 4x plus 7 all over x minus 10 is all real numbers. We can't list them because there's infinitely many of them, except x equals 10. So if we were to look on a number line, right, here's 0, I don't know, 10's over here somewhere. Right, we can put any number to the left of 10 in. We can put any number to the right of 10 in. We just can't put 10 in. So this is how we would graph the domain of this rational expression. Any number that is highlighted in pink on this number line, which would be everything except for 10. So all real numbers except 10 is the same thing as this picture. Interval notation, how we would write this. To write all numbers to the left of 10, you use interval notation. You go left to right, just like you read. So this arrow right here means negative infinity. This arrow right here means positive infinity. So the domain is from negative infinity all the way up to 10. Always use a parenthesis around negative infinity. We're not including 10, so we have to use a round parenthesis. So this represents all the numbers to the left of 10, and all the numbers to the right of 10, well, you start with 10 and you end with infinity. Use a round bracket when we don't include it, and then we use what we call the union symbol. So this is interval notation. Right, so that means this. Set notation, we don't typically use this until we're in higher level math. I use it because I really think it's just a lot easier. Set notation, use the curly bracket and you put the input variable in, and then you put a straight line or sometimes a colon, and then you talk about how the variable behaves or what the conditions on the variable are after this notation. So here, x cannot be 10. So this, all real numbers except 10, looks like this on a number line. This is what it looks like in interval notation, and that's what it looks like in what we call set notation. Actually, if I'm correct, I think your book might use set notation. Alex doesn't, but we definitely use it as we move up in our math classes. All right, so let's try another one. Let's look at this rational expression. determine the restricted values, and then from that information, let's determine the domain. Find the restricted values and then determine the domain. So the restricted values, now be careful that you don't confuse these two. The restricted values is what you're not allowed to put in. The domain is what you are allowed to put in. So they're literally opposites of each other. So, oh, look at this. We have to solve this quadratic equation. So to find the restricted values of this rational expression, we have to determine the values that make the denominator 0. So we just set the denominator equal to 0, and you can solve this however you want. I noticed that this factors. Oftentimes in this section, more often than not, these expressions are going to factor. So before you jump to the quadratic equation, which you're always welcome to use, try to practice your factoring skills. So notice x squared minus 5x plus 6 is equivalent to x minus 3 times x minus 2. And let's just double check. Product of the first. Yep. Product of the last. Yep. Inners and the outers give me 5. So this factor tells me 3 is a restricted value. And this factor tells me that 2 is the other restricted value. So therefore, with the restricted values are 2 and 3. We're not allowed to put those in. Those are our restrictions. Thus, the domain of this expression is, and this is probably the last time that I'm going to write it in words, all real numbers except 2 and 3. So notice these are opposite things of each other. The restricted values are 2 and 3, though the domain is everything except 2 and 3. So let's just practice doing this on a number line. If we look at 2 and 3 on the number line, this says I can pick any number to the left of 2. I can pick any number between 2 and 3. Don't forget there are millions of numbers, infinitely many numbers between 2 and 3. And then I can pick any number to the right of 3. I just can't use 2, and I just can't use 3. So all real numbers except for 2 and 3, we write it this way. This is what it looks like in a number line. Interval notation. Remember, the arrow to the left represents negative infinity. The arrow to the right represents positive infinity. So we go from negative infinity to 2. This open circle says we use the round parenthesis. So all these numbers to the left of 2 is represented with this interval. The numbers between 2 and 3 are everything between 2 and 3 with round parentheses. So open circles correspond to round parentheses. And then everything to the right is 3 to infinity. And then we're going to use the union symbol. Okay. Set notation, the set of all x, except for 2 and 3. All right, so make sure you follow directions on how Alex wants this answer. And be careful of the question that you're being asked. Here it said to find both the restricted values and the domain. But notice the next question says just to determine the domain. But in order to determine the domain, we have to find the restricted values. So we find the RVs first. And that's what's going to tell us what's going to make the denominator equal to 0, which is not allowed. So you might think, oh, and you pop out the quadratic formula. But again, try your factoring skills. In this section, a lot of this stuff often factors. These problems work out nicely. I'm thinking if I put 3 here and 1 here, I can get 3 x's and then 2 x's. So plus and minus, right? So make sure you work on your factoring skills, especially if you're moving on to Math 172. The product of the first is 2x squared. The product of the last is negative 3, and then positive 3x's and minus 2x's gives me that. Woohoo! So now my first factor, this one's not as obvious. I need to know what would make this little factor 0. In other words, 2x plus 3 is 0. So 2x equals negative 3. X equals negative 3 halves. Restricted values do not have to be whole numbers. What makes x minus 1 0? X equals 1. Now remember, this is not the domain. This is the opposite of the domain. These are the restricted values. So the domain is, I'm going to use set notation first. The set of all x is such that x does not equal negative 3 halves or 1. And you'll ask to be It might ask for the restricted values, but I'm thinking in Alex it asks you to use interval notation. So interval notation, if you're struggling with interval notation, I suggest you just use a number line. Put the numbers on the number line, -3/2 and 1. Put circles on those numbers that x is not allowed to be. And then draw arrows to the left and the right of the circles. And then if you have more than 2, if you have 2 or more, look at the region between the circles. Remembering that the left is -infinity, the right is positive infinity. So this is going to be -infinity to -3/2. We always use parentheses around infinity, and we use parentheses that correspond to an open circle. So this represents all the numbers to the left of -3/2. All the numbers between -3/2 and 1 would be represented with this interval. Now notice we go left from right, -infinity, 3/2, and then 3/2 to 1, -3/2 to 1, and then the 1 to infinity. Here we go. This would be the domain. This is what x is allowed to be. So this is saying x can be anything except for -3/2 and 1. Here, this is the equivalent interval notation. Good job. All right, so now let's talk about simplifying rational expressions. I'm sure at some point in your mathematical career you have simplified rational expressions, maybe not to the extent that we've done it. We're going to do it today, but let's look at the simple expression 15/40. My guess is that you can simplify 15/40, and I'm going to break it down. 15/40 is not simplified because 15 and 40 share a common factor of 5. So I'm going to pull out the common factor, and I'm going to write it like this, right? 5 times 3 over 5 times 8. And then we cross off that common factor of 5. And then what remains is 3/8. So therefore, 15/40 simplified is 3/8. Now make sure you check your final answer. Does 3 and 8 have any common factors? Obviously, other than 1. The answer is no, so that would be my final answer. Now this is really super important. We can only cross off common factors in the numerator and the denominator. So let's suppose, what do I mean by that? Let's suppose I had 15/40 equals 5 plus 10, right, over 5 plus 35, right? That's a true statement. Can I cross these off and call this 10/35? Is this true? Well, I don't know. Let's take a look. Maybe it's not obvious that it's not. But if I do 15 divided by, whoops, let's get out of there. 15 divided by 40, I get 0.375. So this is 0.375. And 10 divided by 35 is 0.2857 forever. So these are not equal. You may not do this. You cannot cross off these 5s. Even though going from here to here is true, you may not cancel these common 5s out because you can't cancel out common terms. Right? This is a common factor. So keep that in mind. You're like, of course, this is super simple, but I'll see all the time students will make the mistake of doing something like this, x plus 1 over x plus 2, and they're like, oh, let's cross these off, right? And that just equals 1/2, right? No, do not do this. You may not cross off. These are terms because the 1 in the x and the 2 in the x are separated by addition. Don't do this. Bad things happen when you cross off common terms. All right, so let's take this to the next level because simplifying a rational expression that's just numerical is easy. We've done it. We're now going to take it up a step because this is algebra, and algebra means we are working with numbers. All right, so simplify 2 over 6x minus 10. So what we do is we look for common factors in the numerator and the denominator. So the only thing we have in the numerator is 2 and 1. So can we pull a factor of 2 out of the denominator? Well, we can. If we pull 2 out, we get 3x minus 5. So now factors may contain sums and differences, but this is 2 times the number 1 over 2 times this factor. And we can now cross off that common factor. and call this 1 over 3x minus 5. So therefore, 2 over 6x minus 10 simplified is 1 over 3x minus 5. What is the restricted value? Take a minute, see if you can figure it out. The restricted value would be 5/3. You can either set 6x minus 10 equal to 0, or you can set this equal to 0, but in either case you get the restricted value of 5/3, so we're allowed to put anything in this expression except for 5/3. All right, let's try the next one. 2x plus 2 all over 8x squared plus 8x. All right, let's factor the numerator and the denominator completely, numerator and denominator completely, going all the way back to the beginning of chapter 6. 2x plus 2, the only thing we can do is pull out the common factor of 2. We pull the 2 out of here, we're left with x. We pull the 2 out of here, we're left with the 1. Right, and here we can pull out 8 and x. If I pull out 8 and x, I'll have x left here, plus, now we have to, if you start with 2 terms, you have to have 2 terms in the factor, so x plus 1. Oh, look, factors that can be canceled may have addition and subtraction. This is 2 times this whole thing, and this is 8x times this whole thing. So we're allowed to cross off that whole thing because it is a factor. A factor may have addition and subtraction. We have to be able to cancel out the parentheses and the addition and the subtraction. So 2x plus 2 over 8x squared plus 8x can be simplified down to 2 over 8x. But we're not done because ax also has a factor of 2. So I can write 2 as 2 times 1 and ax as 2 times 4x. Cross off the common factor of 2 and 1 over 4x. So that would be my final answer. 2x plus 2 over 8x squared plus 8x simplifies nicely down to 1 over 4x. All right, given a rational expression, if we looked here, you would note that the restricted value would be 0. But if we looked up here, we would get other options besides 0. Actually, even if we looked in its factored form, right? So here, 0 and -1 would be a restricted value. So if we set the actual original denominator equal to 0, we factored out the 8x. The first factor tells me that the restricted values would be ax, x equals 0 would be a restricted value, and this factor tells me -1 would be a restricted value. Notice when we simplified the expression, we can put -1 into the simplified version, but that doesn't mean -1 is not a restricted value. When you're given an expression and you're asked to simplify and find the restricted values, or if maybe you're just asked to find the restricted values, but you can simplify it, you always find the restricted values before you simplify, because you may lose a restricted value once you simplified. Here, it appears as if we can stick -1 in, but because this is the problem we started with, -1 is a restricted value. So to determine restricted values, you must determine them before you simplify the expression. So here I say determine the restricted values in the domain and then simplify. So we're going to set the denominator equal to 0. We're going to use our factoring skills. So take a minute. Let's say x and x. Multiply to get 12. Add to get -8. 6 and 2. There we go. Yep, because that's going to give me -8, and the product would be 12. So the restricted values are 6 and 2. Therefore, the domain is equal to any value of x except for 2 and 6. X cannot be 2 and 6. Interval notation, again, I'll put it on the number line. You don't have to do this if you're getting the hang of it. It's everything to the left of 2, everything between 2 and 6, and everything to the right of 6. We can't use 2 and we can't use 6, so we indicate that with open circles. So this left arrow indicates negative infinity. So everything to the left of 2 is negative infinity to 2, not including 2. Between 2 and 6, 2 and 6, and then 6 to infinity. So there's the domain. Now let's simplify. X minus 6 over x squared minus 8x plus 12. And we are going to factor, we already factored the denominator. And it is x minus 6 over x minus 2. Well, we can pull out, we can imagine there's a factor of 1 right there. We can cross off these common factors and get 1 over x minus 2. So notice if we looked at the simplified version, the restricted value, only restricted value we see in the simplified version would be 2. So we lost the restricted value of 6. So remember to determine the restricted values before you simplify. All right, one last problem. So this looks very similar to the previous one, but notice that we have a switch in the numerator. So what we're going to do is we're going to simplify. We're going to factor the denominator. All right, so we already know we factored it in the previous problem. We have x minus 6 and x minus 2. Now be careful, when we switch the order of subtraction, the factors are not the same. 6 minus x is not the same as x minus 6. So you'll come across these problems on occasion. You may not cross these off, it's not true. But we have this cool thing called the polynomial's opposite property, and that's our trick here. If you want to switch the order of subtraction, the trick is to factor out a negative 1. So if you have a minus b, but you want b minus a, factor a negative 1 out, and then you can switch the order in which you subtract in the parentheses. So for example, let's suppose we have 6 minus x, but we need the factor x minus 6. Factor the negative 1 out and write x minus 6 in the parentheses. Now just double check. If you were to check, negative 1 times x is negative 1x, and negative 1 times negative 6 would be plus 6, which is equivalent to 6 minus x. So that is our trick. When we have a factor that looks, if this was addition, this wouldn't be a problem. X plus 6 is equal to 6 plus x. We can switch the order in which we add because addition commutes, but subtraction does not. So here, in order to switch the order in which we subtract, we're going to go back up here. I'm going to write it here, and we need the factor of x minus 6 in the numerator. So I'm going to factor a negative 1 out, and 6 minus x is equivalent to negative 1 times x minus 6 all over x minus 6 times x minus 2. Cancel off the common factor. Negative 1 over x minus 2. Woohoo. All right, just one more little itty-bitty side note. Just because you may see the answer different in your book, this is a perfectly acceptable answer, and Alex should accept the answer. Notice that we've got a couple negatives going on here. We have negative 1 up here, and we have x minus 2 down here. Sometimes authors don't like seeing negatives, especially if it's a constant in the numerator. So they may multiply the numerator and the denominator by negative 1. If we do this, negative 1 over x minus 2 becomes positive 1. And then negative 1 times x minus 2, we'd go to the polynomial's opposite property, is 2 minus x. So both answers, negative 1 over x minus 2 and 1 over 2 minus x, are correct. They are algebraically equivalent. They mean the same thing. Your book would probably write this. Alex would take either one. Right, that being said, here's your to-do for 9.1. Read 9.1. exercises 1 to 59 odd. I know that's a lot of problems, but the more you do in 9.1, the more exercises you do, the more comfortable you will be with this. I would really get a jump on this before you start doing the next couple sections, because you need to know how to simplify before we start multiplying and dividing and all that other stuff. Alex, you can get a jump on your 9.1 topics. Check Blackboard for your percentage for next week. And that's it for now. I will see you in section 9.2.